In the last class, we mainly looked up to electronic devices and fabrication of solar cell. Today we are going to start to look at up to electronic devices, and the first device we are going to focus on LED, that is a light emitting diode. If you remember, there are mainly two kinds of devices, those in which you have an injection of carrier that recombine in order to give light. This could be in infrared region, visible region. You also have a second kind where you shine a light onto the material and get an output in the form of electric current. So LEDs and laser belong to first kind of devices. Later we will look photodetector and solar cell, which belong to second kind. And we know that LED belong to luminescent device. So what is a luminescence? Which means optical emission due to electronic excitation, which means due to excitation of electron, there will be a creation of electron and hole pair. Example, photoluminescence. We can excite electronic excitation using light. Photoluminescence means if you incident light on a material, there will be a creation of electron and hole pair. Another example of luminescence is cathodoluminescence. Using electron beam, a beam of electron, we can create electron and hole pair. And also we have electroluminescence. Using electric field or electric current, we can create electron and hole pair. LED is an example of electroluminescence device. Now, it is a forward biased PN junction which emits light radiation. When suitable forward bias voltage is applied on it, and the working principle of LED is electroluminescence process. This process can be explained in three steps. The first one is electronic excitation, or the first you say excitation process, which means when a suitable forward bias voltage is applied on LED, this voltage excites the electron from valence band to the conduction band by forming electron and hole pair. And the second one is recombination process. The second process is recombination process. When the applied forward bias voltage is greater than the potential barrier across the junction, as a result, there will be a recombination of electron and hole take place. During this process, excess energy of electrons emitted in the form of heat or light. And the last process take place in the electroluminescence process is extraction process, which means an output. In this process, emitted light pass out the depletion region and reach the observer. The light can be emitted, and this light can be, the wavelength of the light or photon can be calculated by using lambda is equal to hc by Eg. Now, the phenomenon of electroluminescence was first discovered in 1907, and the first gallium arsenide LED was made in 1962. The material used in LEDs are direct band gap semiconducting material. Here the LED chip, which means this is the LED chip PN junction, and then here there will be a cathode and this is the anode. This is the anode and this is the cathode, and this is you call it as reflecting cup, and therefore the output here, the light is emitted or the light is emitted from the chip. Now, in LED, there are different kinds of transition have possible. In general picture, we are focusing the first kind of transition, that is the interband transition. Here, let us consider the band diagram. Okay, the first one is interband transition, in which both electron and hole are at the edge of the conduction band and valence band. Here there will be, for example, here the holes are at the edge of the valence band and the electrons is at the edge of the conduction band. And also have electron and hole deep, which means here you consider the electron is a deep, here electron is at the deep, here the hole is at the deep. The transition from conduction band to the valence band, the transition at the edge of the valence band and conduction band, these type of transition you consider as the interband transition. Okay, in the second kind of transition, you call it as the defect transition. Suppose if the material is doped with some impurities, these basically cause the defect state in the band gap. Suppose if the donor type impurity is added, then the donor level is very close to the conduction band. Suppose here there will be a donor level line is there here. Suppose you consider the donor level is very close to the conduction band. We could also have a acceptor level which is very close to the valence band. Here there will be a, just you consider it as, here there will be a level, you call it as acceptor level, very close to the valence band transition. Now the transition take place between defect state. Okay, here also possible. For example, donor level transition to the acceptor level, donor level transition to the valence band edge. Okay, in this type, or donor level to acceptor level, this transition is also possible. This kind of transition you call it as defect transition. And the third kind of transition is intraband transition, in which suppose the electron in the bulk of the conduction band, bulk means here there will be electron. Okay, the electron within the bulk of the conduction band and go to the edge of the conduction band. Okay, similarly, suppose if the hole is in the bulk of the valence band and goes to the edge of the valence band, this type of transition also possible, and this type of transition you called it as intraband transition. Deep means here, deep here the electron is at here and the transition take place and comes to the edge of the conduction band. In these transition, not all of them are radiative, only some of them are radiative transition depending upon the band gap and the characteristic of the material. In case of LEDs, we want to maximize the radiative transition and minimize the non-radiative transition. In order to increase the efficiency of the device, we can understand the physics behind this type of transition. Now, the material used in LED or direct band gap semiconducting material, you know that in a last class also we discussed what are the direct band gap semiconductor. Here the material are using in LED. Suppose if we use the material aluminum nitrate, and then the forward voltage of LED is from 3.1 to 4.4 volt, then there will be a less than 400 range of wavelength. The light is emitted, they could be comes under ultraviolet region. Indium gallium nitrate, the range is here given, and the wavelength and the resultant emitted photon or light will be violet, and then blue, then green. Here there is a range of wavelength is there, and here the varying voltage with respect to different material used in LED. Okay. Now, the very important concept here you have to understand, that is the working principle of PN plus junction LED. How LED work? Okay, consider a simple PN plus junction. Here N plus means, this N plus means N region is heavily doped. Okay. Now, when we form the junction, the depletion region is mostly on P side. Okay. When we made a junction of same material, the over all the band gap is the same. If we use the same material, the overall band gap of material is the same. Okay. Now, suppose if we consider, suppose here, if we use, you consider this is the band diagram. Here you call it as the EV. EV means energy state of valence band, EC energy state of conduction band, and here there is a Fermi level. Okay, suppose if P type of a material we are using, the Fermi level lies just above the valence band, here just above the valence band. Suppose if we use N type of material, the Fermi level lies just below, okay, just below the conduction band. What is the Fermi level? It is nothing but the highest energy level that an electron can occupy the absolute zero temperature. Now, at equilibrium, when we made a junction, the Fermi levels are line up. Now, at equilibrium, if we made the junction, if you consider the separate P type and N type, in P type, Fermi level just above the valence band, and in N type, Fermi level comes just below the conduction band. If you made a junction and then at equilibrium, the Fermi levels are lines up. Okay, and then we have, due to this junction, we have a built-in potential or contact potential. That potential is EV0. Due to this junction, a potential will be developed. That potential you call it as contact potential or inbuilt potential. If the junction is forward bias, suppose if the junction is forward bias, that is the P type is connected to positive of the battery and N type is connected to negative of the battery. If the junction is forward bias, we will reduce the contact potential so that we can inject the minority carrier on both sides, and the junction potential becomes E into V0 minus V. In this situation, the whole this contact potential EV0, if we apply voltage is V, then it reduces, then it becomes E into, take the common of electronic charge E, this becomes V0 minus V. Okay, these electrons and holes recombine in the depletion region. This contact potential get reduces. Here they start the electron here, and then here there will be a depletion region, that is a region will be developed in the junction, is nothing but the contact potential. If we are applying forward voltage, then these inbuilt or contact potential reduces, then it become E into V0 minus V, then electron and holes recombine in depletion region. If the material is direct band gap semiconductor, then this recombination will dominantly produce light, and its energy of light is just given by the band gap of the material, that is the EG. This energy is nothing but which is equal to band gap of the material. If you want to calculate the emitted light, lambda is equal to Hc by Eg, and it is a spontaneous process, and this whole process is spontaneous. Okay, And the another important, you already know the working principle of PN junction. How, suppose P type and N type, if we made the junction, and then there will be a contact potential. If we applied forward bias voltage, and then it reduces the potential, the barrier will be reduces. Suppose now this is circuit diagram. Applied voltage, milliammeter. This is the LED, and you have to measure the voltage if you want to study the forward current and voltage characteristic, which means how current vary with respect to voltage. Suppose here now at some forward voltage the potential barrier is altogether eliminated and the current start flowing in the circuit. It becomes complete circuit. If the barrier is reduced, they can current easily move in this junction. Easily there will be, it act as a circuit diagram. Here there will be a recombination of electron and hole take place at this depletion region. Now it seems that at first the current increases very slowly. Suppose if you make a table like the voltage vary in a very small values, that is the 0, that is 0.25, 0.50, 1 point or 0.75 or 1 and 1.75. In this way you can increase the very small value 0.25 values and then up to the 1, and then the current becomes 0. Initially becomes 0. After above 1 and 1.5, here there will be a small increase in current. Up to that value, the current becomes 0 because the barrier is there. After increasing the forward voltage, the barrier goes on reduces. Here they start the current. Here the current will be, you can note down, if the LED is just glow, and then further you increase the voltage and then linearly the current also increases. LED also, the brightness of LED also increases. This is the, if we draw the characteristic or a graph of current versus voltage, then it becomes initially at some voltage up to 1 and 1.1 up to the 1, and then this current becomes 0 and gradually they increases. If you draw a tangent in this line, and this voltage is the threshold voltage, the voltage at which the LED is just glow. They starting, the current meter start the reading. We can note down the reading also, and we can see the LED is glowing. Okay, LED is initially started or on. This voltage you call it as knee voltage or threshold voltage. This is the IV characteristic of LED. Thank you very much. Thank you.